So we're doing numerical integration. Let's review what we talked about last time. We did talk about the left and right hand rules, and we will talk about those again today, though not right at the start. We've got the trapezoid rule, or trapezoidal rule, if you prefer, that says if you're integrating over an interval from A to B, or, well, let's go ahead and use node notation, x0 to x1, you could represent this integral as an approximation that comes from the area of a trapezoid plus some error term, though, word of warning, the error term is only likely to be small in absolute value if the interval from x0 to x1 is relatively small. H is going to be the distance between x0 and x1. I'll write it as x1 minus x0. I'm implicitly assuming that x0 is less than x1 when I write that. And that will be a positive number. Yeah, the book writes it this way: h over 2 times f of x0 plus f of x1. And then that's the approximation, plus the error term, though the error term has a minus sign, minus h cubed over 12 times the second derivative of the function you're integrating at some unspecified number xc between x0 and x1. Xc is somewhere in the interval between x0 and x1. In general, you're not going to know what xc is. This is a theoretical result here written this way. But even if you don't know what xc is, if you can bound the second derivative for the function on the interval in question, you can come up with an upper bound for the absolute value of this thing. And if h is relatively small, if x0 and x1 are close together, yeah. I mean, if h is like 0.5 or 0.1 or something, or maybe smaller, h cubed is going to be really small. Divided by 12 is going to be even smaller. And as long as that second derivative doesn't get too big on the interval, which in theory it could, but as long as it doesn't in most ordinary situations, then in absolute value, this error term is going to be relatively small. Yeah, that's the error term. Well, maybe I should say this is the error term right there. Okay. And then we also had Simpson's rule, which, well, instead of using 2 nodes and a linear approximation to the function, we're using 3 nodes and a quadratic approximation to the function. We've got x0 less than x1 less than x2, and in fact, we want those to be equally spaced. H should be this x1 minus x0 and also x2 minus x1. So the entire interval is of length 2h. We are integrating from the leftmost point to the rightmost point. And Simpson's rule in this context is written as h over 3 times f of x0 plus 4f of x1 plus f of x2. See if I can remember the error term correctly. Minus h to the 5th over, I believe it's a 90, times the 4th derivative of f evaluated at some unspecified number xc in the interval. There's your approximation. There's your error term. And again, c is some unspecified number in the interval, this time from x0 to x2. And again, think about this. If h is small, less than 1, like 0.5 or 0.1 or 0.01, h to the 5th is going to be even smaller. Divide by 90, it's going to be a couple orders of magnitude even smaller. As long as that 4th derivative doesn't get too big in absolute value, then you can expect a pretty small error. But no guarantee of small errors here. If your interval of integration is large, if h is bigger than 1, especially if it's significantly bigger than 1. There's no guarantee that these error terms are going to be relatively small. Your approximation could be bad, you might say. Do notice, again, that these error terms have minus signs. I probably should include the minus sign in there. So, for example, with the trapezoid rule, if the second derivative on the interval happens to be positive, then the error is going to be negative. And if the second derivative is negative, then the error is going to be positive. Does that make intuitive sense? Well, our main example here, again, is the natural log function. And we'll continue thinking about this example again today. Ln of x is defined to be, well, one way of defining the ln of x is defined to be the integral from 1 to x of 1 over t dt. So my f function, f of t is 1 over t, though when I use technology, I'll just write it as an f of x. And that function is decreasing and concave up. And the trapezoid rule, over whatever interval you're talking about, does approximate the area under the curve by using a linear approximation. It's interpolation there. We're using a degree 1 Lagrange interpolation, which is just a straight line connecting the points, the secant line there. And yes, what the trapezoid rule is really doing is it's using the area of that trapezoid to approximate the area under the curve. You can see if the graph's concave up like this, and it is the fact that it's concave up, not the fact that it's decreasing. The trapezoid rule is going to give an area too big, an estimate too big. Since the error is actual minus approximate, if the approximation is too big, you're going to be subtracting a bigger number. You're going to get a negative error, which is confirmed by that minus sign there. Evidently, with Simpson's rule, you get a negative error, a too big approximation, if the fourth derivative is positive. But how do you visualize the fourth derivative? I don't really know of any easy way to do so, right? How do you visualize a fourth derivative? I don't know. It's not real easy. I've never thought about it, to tell you the truth. So maybe you can't really visualize it. But do realize one other thing this means, though, is that if your function that you're integrating is a cubic polynomial or a quadratic or linear, Simpson's rule gives you the exact answer because the fourth derivative will be 0. Simpson's rule will give you the exact right answer if you got a cubic polynomial or lower degree. Kind of cool. But of course, with cubics, we could always just use the fundamental theorem of calculus anyway. So what are we going to do today? A number of different things. Just for practice, we're going to implement these on a spreadsheet, just to see how we could maybe do it on a spreadsheet. Then we're going to implement them on Mathematica using the approach in the other video that I suggested you watch, that is the approach that we teach in calculus, that I call an empirical approach, where the formulas you see here are not going to be exactly what we use, but they are equivalent. And we should use the empirical approach to experiment and look at how the errors behave as the number of nodes increases, as the number of subintervals that you use increases. We are briefly, perhaps if we have time, going to talk about something called Monte Carlo integration. I'm not sure if we'll have time for that today. If not, we'll wait till next Tuesday. And then I do also even want to introduce differential equations today. So there's a lot to do here. What we're about to do with this spreadsheet is use what are called composite numerical integration formulas, where we're effectively adding the trapezoid and Simpson's rules over more than just one interval in the trapezoid rule case or two intervals in the Simpson's rules case. It's like we're piecing together. It's like a linear spline in the trapezoid rule case and a quadratic spline in the Simpson's rule case instead of cubic splines. Kind of like that. Let me just tell you what the answers are for the formulas. They're right here. I will share this notebook on Moodle after class. For the trapezoid rule in general, you use this formula, where what is h? H is the length of each subinterval. It's b minus a over n. h is b minus a over n. We're trying to approximate the integral of a function from a to b here. H is b minus a over n. X0 is a. X1 is a plus h. X2 is a plus 2h. X3 is a plus 3h, etc. In calculus, this is what we do in calculus. Sometimes we use the letter delta x instead of h. Xn is a plus nh, and if you replace h with b minus a over n and cancel the n's, that does simplify to b. H over 2 times this summation where f at the 0th node and f at the nth node have a coefficient of 1. And all the other function values at all the other nodes have a coefficient of 2. Where is this weirdness coming from? It's coming from adding a bunch of these kinds of things together. And noting that for the endpoints where the intervals overlap, where they touch, you're going to add the function values twice. That's what's going on. You're really doing h over 2 times f of x0 plus f of x1 plus h over 2 times f of x1 plus f of x2 plus etc. H over 2 times f of x n minus 2 plus f of x n minus 1 plus the last term would be h over 2 times f of x n minus 1 plus f of x n. You can factor out an h over 2 out of all that. F of x0 only occurs once. F of x1 occurs twice, here and here. So you need 2 of them. F of x2 occurs twice, here and someplace right there where I didn't write it. So you need a 2 in front of it, etc. F of xn minus 2 occurs twice. F of xn minus 1 occurs twice. But f of xn only occurs once. That's where this general trapezoidal rule comes from. In a similar way, there's a general Simpson's rule. Looks like this. You do need in this rule here for n to be even n, okay? But h is still b minus a over n. You go h over 3 times this expression. The 0th and nth nodes give you function values that have a coefficient of 1. Then in between that, the coefficients alternate 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, etc. Starting with a 4 at the first node and ending with a 4 at the n minus first node. Okay. So are you writing those down? You want to remember those now? We're about to use a spreadsheet. Last time we were focused on approximating ln of 1.5. Let's make it a little harder, so to speak, this time. Let's approximate ln of 5. How? By integrating f of x equals 1 over x from x equals 1 to x equals 5. Of course, we know that equals ln of 5 by the fundamental theorem of calculus, and what we emphasized last time, that was we were thinking of defining ln of x that way. But now we're using numerical approximation to approximate it. Of course, you know, we've got the technology, we have the power, we can have the technology give us a good approximation as well. You can see there, ln of 5 is about 1.609437912. That's our quote unquote exact value. Of course, it's really an approximation as well. We should specify what h is. That would be good. H is b minus a over n. What should we use for n? I suppose we should say what we want n to be. Let's pick n to be 4, which means we got 5 nodes, right? Starting with the 0th node. And 4 subintervals, an even number of subintervals, so we can use Simpson's rule in this form here. H is going to be b minus a over n. Yeah, we'll go ahead and see how this does. H is going to be 1. 5 minus 1 over E2. H is going to be 1 in this case. Yeah, okay, maybe I should use something bigger. Let's for n. Let's use 8. So H is 0.5. Okay. I could make a column for the I values, the xi values, f of xi. That's probably a good way to start. I is going to start at 0 and go up to 8. Take what's in A6 and add 1 to it. Copy and paste it down. One more. Xi starts at 1 and then keeps going up by h. So here I'm going equals B6 plus $E $3. Using dollar signs to keep the cell reference fixed. I get 1.5 up through 5 in the end. And then I'm evaluating the function 1 over x by doing this. 1 over B6. I could do an autofill, but I guess I'm not. Let's go ahead and do the left and right hand rules here as well. I hope it's pretty clear what to do. A left-hand rule is going to add up all the function values at the left endpoints of each of these 8 intervals and multiply times h, because you're really finding areas of rectangles in that case. Remember doing that in calculus? Starting using the left endpoint of each interval. So I could do h again as in cell E3. I could do equals E3 times the sum of C6, not through C14, but C13. I don't want to use that rightmost node. The 8th interval I'm using still the 7th node to figure out the function value, the height of the rectangle. This is a decreasing function, right? 1 over x. These rectangles, if you can imagine in your mind, are going to be above the curve because it's decreasing. It's going to give us an over approximation to the natural log of 5. Error is going to be too big. So you can see we get 1.828968. Yep, that's too big. The actual values in cell E1, so the error, not error, E1, okay, equals E1 minus our approximation. It's a negative error because the approximation is too big. Right is going to give us an approximation that's too small. We use the right endpoint of each interval. We use h from cell E3 again, times the sum of C7 through C14 instead of C6 through C13. So the very first interval, we're using the right node x1 to figure out the height of the rectangle. Graph is decreasing. That rectangle is going to be under the curve. All of them are going to be under the curve. This is going to be too small, and the error is going to be positive. Again, where's the function value? It's in E1. Okay, so there's a quick way to do left and right approximations. What about the trapezoid rule? If we're going to use the formula we were just looking at, this one here, what's a convenient way to do that? Well, one way to do that is to just use this column. Maybe it would also be useful to make another column of 2 times function values that, or maybe I should do something like this. Maybe I want to have trap summands column or something like that. What am I after here? I'm after function values at the 0th node and the 8th node. See what I'm doing here? So right there in cell D6, that's going to be f of x0. The coefficient of that in the trapezoid sum is 1. Same for the 8th node down here. So I just copy and paste down there. But in between, I need to multiply by 2. It's one way to do this. Maybe I'd also want separate columns where I have coefficients of 2 just for the ones that I need. So here I'd do equals 2 times this value. Copy and paste that down for these middle nodes like this. And maybe I should have added a column in here or put this over to the right one. I will try inserting a column. Oops, not that way. Insert one left. So I can put the word trap here is the reason I did that. And now I can just not just add those, right? But also multiply by h over 2. What's going to happen? The graph's concave up. We saw the line segments. The linear approximations are going to be above the graph because the graph's concave up. Approximation is going to be too big. Error is going to be negative. Let's see if that happens. So H again is in cell, well, now it's in cell G. Maybe I want to delete this column. Delete column. Okay, now H is in cell F3. Don't forget to divide that by 2 now. And here in the formula, we need to use all these values, not just the first 8 of them or the last 8 of them. We need to use all of them. So I sum E6 through E14. I used all of them. There's our answer. You can see it is slightly bigger than that. Exact value there's an F1. So the error is F1 minus this is a small negative number. But you can see the error is significantly closer to 0 than it is for the left and right hand rule for n equals 8 here. You know, this is in absolute value about 10 times smaller than both of these. It's doing about 10 times better. And then maybe I want simp summands. Summands are the terms that I'm adding. Or the 0th node and the last node, again, your coefficient is 1. What happened there? I thought I copied and pasted. There it goes. Okay. Look at the formula again. For the 0th and nth nodes, the coefficient is 1. For the middle nodes, the coefficients alternate 4, 2, 4, 2, 4, 2, etc., starting with a 4 and ending with a 4. So the odd numbered nodes have a multiplier of 4. So I'm typing equals 4C7 there. For the function value at the first node, I will also copy and paste that to the function value at the 3rd node, at the 5th node, and at the 7th node. Bit strange, but it's coming from adding together the Simpson's rule approximations on each interval. And it just turns out that the odd nodes have 4 multipliers and the even ones have 2 because the even ones are the boundaries between the 2 different quadratic splines, you might say. So those get added twice. Yeah, for these even numbered nodes in between, you multiply by 2, not 4. Copy and paste that to the 4th node and the 6th node. And then, again, H is in cell F3. Divide H by 3 this time instead of by 2. F3 divided by 3 times the sum of F6 through F14. And this should be the best approximation. There it is. Is the error positive or negative? It looks like it's going to be negative. It's slightly too big. The fourth derivative of this function must be positive, which makes sense. 1 over x is decreasing. It's got a negative first derivative. It's concave up. It's got a positive second derivative. And if you imagine continuing to take the next derivative would be negative, the next derivative would be positive, right? X to the negative 1 has a derivative of negative 1, x to the negative 2. Negative x to the negative 2 has a derivative of positive 2x to the negative 3. The sign in front keeps alternating. So we have a positive second derivative, which leads to a negative error with Simpson's rule. But wait a minute, don't those error terms only apply for the simpler case? Yes, but they can be combined just like the formulas can be combined over bigger intervals with more subintervals. What's the result when you do so? Let's summarize what the errors are. Here's where I wrote them in this Mathematica notebook that I'm going to share. It's in the section labeled Understanding Numerical Integration Errors. I'm not sure if we'll have time for the probability example here that I'm referring to, but here's an error bound for the midpoint and trapezoid rule. I haven't talked about the midpoint rule today yet. The trapezoid rule has an error bound that looks like that. Notice we've got the absolute error, the absolute value of the actual value of the integral minus the trapezoid approximation for a given value of n is less than or equal to m times b minus a cubed over 12n squared, where m is an upper bound for the second derivative of the function on the interval. That's worth writing down. Is it in the book? Yes, it is. Though it doesn't quite look the same in the book. It's in section 4.4. Oh, where'd my, there it is. So in the book, the error term for composite trapezoid rule, there's our summation times h over 2. Here's our error term. It doesn't look the same, does it? Well, first of all, one difference is that it's not written as an inequality. It's written as an exact error term. We got equality there. Mu is some unspecified number in the interval. It's kind of like a c, but now it's over the entire bigger interval, so the book is using a different letter. For some unspecified mu, we've got equality here. But as we've always done, since we can't typically find the c or the mu, we end up just trying to bound, in this case, the second derivative of the function over the entire interval. And m is an upper bound. You do see a b minus a in there, but you also see an h squared. Well, hey, h is b minus a over n. So really, if you replace that h with b minus a over n, you get b minus a over n squared. You would get b minus a cubed, and then you get a 12n squared in the bottom. It is the same thing. We're taking absolute value signs, so the negative sign goes away. That's the error in the trapezoid rule. And it can be used. Well, we're about to use it to figure out a guaranteed upper bound on the trapezoid error, say for the function f of x equals 1 over x over the interval in question, for our problem in question, in a few minutes here. Here's an upper bound for Simpson's error. Not surprising, it's based on an upper bound for the fourth derivative of the function over the interval. In the book, it's on the previous page, it looks like this. It is the same thing. Again, replace h with b minus a over n. You'll get b minus a to the 5th power then over n to the 4th power. See, the bottom is still 180. You can read the book's derivations of these things. It's understandable. It's not the hardest thing we have in the book. Actually, they just do it for Simpson's rule here. Let's confirm that these are working for our example. So for our example, again, the function is f of x equals 1 over x to the negative 1 power. The interval in question from a to b is 1 to 5. Might have been more interesting to pick an interval like 2 to 5 or something, because making the left endpoint be 1 makes the m's really easy to find. But we'll leave it at that. The first derivative is negative x to the negative 2, negative 1 over x squared. Second derivative is positive 2x to the negative 3, positive 2 over x cubed. Third derivative is negative 6x to the negative 4. And fourth derivative is positive 24x to the negative 5. Yes, and that is a positive quantity when x is positive, and that's why the Simpson's rule error ends up being negative for this example. You know, how do you take the graph of 1 over x and somehow visualize that somehow the third derivative is negative, but the fourth derivative is positive? I have no idea, just looking at the graph, how to imagine that. But we trust the symbol crunching there and our analysis to realize the third derivative is negative, but the fourth derivative is positive. So if we think about the trapezoid rule one, for trap, we want to bound the second derivative in absolute value. Well, it is positive, so I don't need the absolute value signs. There's the absolute value of the second derivative. It's the same as the second derivative itself. On the interval in question from 1 to 5, what's an upper bound for this? This is a decreasing function of x. It's biggest at the left-hand point when x is 1. This is less than or equal to 2 times 1, or 2 over 1 cubed, or 2 on the interval in question from 1 to 5. If the interval in question were 2 to 5, it would be bounded by 2 over 2 cubed, which would be the same as 1 over 2 squared, 1/4. We can use an m equal to 1/4. It'd be a little bit more interesting, you might say. This would be the m we can use for the error bound of the trapezoid rule. Therefore, the absolute error is less than or equal to m is 2, b minus a is 5 minus 1 to the third power over 12n squared. I'm looking right here. Simplify. That's 2 times 4 cubed is what? 64? 64 over 12n squared. 2 cancels with the 12. 64 over 6 reduces to 32 over 3. 32 over 3n squared is a guaranteed upper bound on the error for any given value of n. When n is 8, what does this become? N squared would be 64. 64 times 3 is 192. 32 over 192 is about exactly 1/6, 0.16 repeating. So 1/6, according to this theorem, essentially, is a guaranteed upper bound for the absolute error of using the trapezoid rule in our problem when n equals 8. Is that what we saw? We saw an error that was much smaller in absolute value, actually. Just a guaranteed upper bound. The actual absolute error could be much smaller. But the theorem gives a guarantee. What about Simpson's? For simp, the fourth derivative in absolute value is the same as the fourth derivative itself on the interval in question is less than or equal to 24 over 1 to the fifth, or 24 on the interval from 1 to 5. Again, that'd be more interesting if we did the interval from 2 to 5, and in fact, we'd get a better upper bound if the interval was 2 to 5, because then we could replace x by 2, 2 to the fifth, 32, 24 over 32 is a much smaller number, less than 1. We get a better upper bound on the error. In the Mathematica document here, we only use that. So the absolute error in this case is less than or equal to m is now 24. B minus a is 5 minus 1 to the fourth power, or fifth power, excuse me, over 180 n to the fourth. Yeah, this is not such a small quantity. 4 to the fifth is 1,024 times 24 is over 24,000. Divided by 180 is kind of a big number here. 136.53 repeating. I'll just write my calculator version of it instead of a rational number without a decimal. Over n to the fourth. When n is 8, what's this going to become? I'm going to divide this by 8 to the fourth. I get 0.03 repeating, 1/30th, as a guaranteed upper bound on the absolute error. And yes, our absolute error was definitely less than that. In fact, significantly less than that. There's this on the order of 0.001, in other words, on the order of 1/1000th. Whereas this is 1/30th. So like a factor of 30 smaller. But again, this gives you a guarantee. It's going to, again, produce better results if our interval were, for example, 2 to 5. Smaller guaranteed bounds on the absolute error. You should be able, I think, I feel comfortable in saying that you should be able to use these kinds of bounds to also solve for minimum values of n to give you guaranteed errors. For example, if you wanted this to be less than or equal to, say, 0.001, how big would n need to be? Solve that inequality for n. You've done those kinds of problems before. No need for logarithms or anything like that. You would just flip both fractions. The inequality would change directions. You'd have to cross multiply and take a fourth root. And then round up. You get a guaranteed minimum value of n based on the theorem. And probably a smaller value of n works, but you want to guarantee based on the theorem. That's what you would want to do. And am I fine in saying you should be able to do that? You've done that kind of thing before with errors previously. Okay. Now what I want to do is review quickly the empirical approach to numerical integration with Mathematica that re-emphasizes these error bounds, and in particular emphasizes the fact that the denominator here depends on n squared, and the denominator here depends on n to the fourth. If you watch that extra video, I emphasize those things in that video. Let me re-emphasize them here now. Same example. Let's do the function f of x equals 1 over x. I'm going to type this into Mathematica. A is 1, b is 4. Enter those things. The left-hand rule can be programmed into Mathematica. If you use the palette with a nice summation here, I can click the summation button. Let I go from 0 to n minus 1, indicating I'm going to start with node 0, then node 1, then node 2, up through node n minus 1. F of xi times delta x, meaning times h. What is xi? It's a plus I times h. What is h? H is b minus a over n. Said that very quickly. You understand what's going on here? Make sure you think about it. Over each interval, I'm taking the left endpoint, which is this thing, plugging it into the function to get the height, multiplying times the width. I'm computing an area of a rectangle, and then I'm adding those up. It's the left endpoint of each interval because I start I at 0 and go to n minus 1. For a right-hand sum, it's the same kind of thing, except start I at 1 and go to n instead. So for the first subinterval, I use the right endpoint, which is x1, not x0. For the second subinterval, I use x2. For the third, I use x3. For the last one, the nth, I use xn. I'm programming these into Mathematica as functions of n. I'll change the name of that one. We could also do this kind of thing. For our example, well, the actual value is the natural log of, oops, I meant b to be 5, didn't I? The actual error is the natural log of 5, but we could type it in as an integral like this. Actual value minus approximate value. Do something similar for a right-hand error. And then we could observe what happens with these errors as n increases. We could, for example, make a table of values of, well, maybe we want to see the integral in there. The integral, numerical approximations. Actually, I can just put my / capital N at the end of these things. Left, right, error left, error right, / capital N to get a numerical approximation. And in my table, I'm going to let n go from, I'll start at 10 and go up. Maybe I should do something else instead. Maybe I should let, well, I'll start n at 10 and go up to it. Okay. Let me start k at 1 and go up to 10. But instead of plugging in k in for these things, I'm going to plug in 10 to the k. The 10 to the k's are going to represent my values of n, but the way I'm doing it is going to guarantee that what I'm really plugging in are first 10, then 100, then 1,000, then 10,000, then 100,000 powers of 10. I probably don't want to go up to k equals 10. That's too much. What, 5? That might even be too much. Okay, let's go 4. Doing a lot of calculations. That might be, okay. So here's the exact values in each case over there, the 1.60944. These are our approximations, left, then right, then the errors. They get better and better as n increases. N is first 10, then 100, then 1,000, then 10,000. These are the errors in all cases. And you can notice, approximately speaking, every time n increases by a factor of 10, from 10 to 100 to 1,000 to 10,000, in absolute values, these errors are going down by about a factor of 10. That turns out to be because if you came up with error bounds for the left and right-hand rules, you'd be dividing by n instead of like n squared and n to the 4th we do with the trapezoid and Simpson's rule. And they're also, especially as n gets larger, approximately opposite in absolute in value. The error for the left is approximately the negative of the error of the right. Therefore, if you average the left and right-hand rules, that should be a better approximation. And that, in fact, is what the trapezoid rule does, is it's really averaging left and right approximations. And I could do this kind of thing. Copying and pasting to make things faster here. And I could make a similar table of values for the trapezoid rule. I know I'm going fast here, but it's stuff that you should get if you slow down and take the time to think about it. and we'll observe what we observe. It's still the same function we're integrating here. Still 1 over x. It's still a decreasing concave up function. Trapezoid rule is going to give you overestimates and negative errors. And again, the table, maybe I should have another column here for 10 to the k. The table is giving you approximations. First when n is 10, then 100, then 1,000, then 10,000. And we can see the errors here becoming smaller and smaller. And in fact, if you look at these numbers carefully, you see that in absolute value, they're decreasing by about a factor of 100 each time. From about 1 times 10 to the negative 2 to 1 times 10 to the negative 4 to 1 times 10 to the negative 6 to 1 times 10 to the negative 8. That's because we're in the error theorem, we're dividing by n squared for trapezoid. And they are negative errors over approximations. Simpson's rule comes from combining the trapezoid rule and one other rule called the midpoint rule, which is not discussed in the book. With the midpoint rule, what we're really doing, well, let's do it with this one here, is we are using for each interval, first, second, third intervals, etc., using the midpoint to determine the height of an approximating rectangle. We're using constant approximations to the function effectively instead of trapezoids. But because we're using the midpoint, it generally does a much better job, and it even does better than the trapezoid rule. To get it to be the midpoint, let's see, I'm going to do this. I'm going to average these xi's here. Where I have an I minus 1 here and an I here. So what I'm doing here is I'm plugging in general, x sub I minus 1 and xi, and averaging them into the function. That's the midpoint in each case. Right? Think about if I were 0. This would be a plus x1 over 2. x0 plus x1 over 2. You're averaging the two. It's the midpoint of the first interval. I know I'm going quick. That's the midpoint rule. What happens when we look at its approximations and its errors? For this 1 over x function, you can see they're positive errors. The midpoint rule for a concave up function gives approximations that are too small, resulting in positive errors. I'd encourage you to look in your calculus book in the section on the trapezoid rule and the midpoint rule. I believe it's chapter 7. And you'll see why the midpoint rule gives two under approximations when the graph's concave up. You can actually think of the midpoint rule as giving you areas of trapezoids as well, related to the tangent lines on a concave up graph, which will be below the graph. Okay, this is stuff you should have seen in the past. You just may not remember it. Notice these in absolute value are going down by a factor of 100 every time and increases by a factor of 10 as well. Again, it turns out because the error in the midpoint rule, you end up dividing by n squared. I actually did have that in this notebook down here as well. Here's the error for the midpoint rule. It's similar to the error for the trapezoid rule, except it's a 24 in the bottom instead of a 12. These errors, not only are they positive, but they're also about twice as small in absolute value as these numbers. The midpoint rule does about twice as good in terms of the size of the errors as the trapezoid rule does. And that's what motivates Simpson's rule in this approach to being a weighted average of mid and trap, where you give mid twice the weight because it does twice as good. And they generally have the opposite signs, not always, but generally. And so by doing this kind of weighted average and dividing by 3, it's like we're adding midpoint twice and trapezoid once, dividing by those 3 numbers. This should be the best approximation of all. And what happens with its errors as n increases by a factor of 10 each time, they go down by a factor of 10,000. What's that? That's about 5 times 10 to the negative, what? 1, 2, 3, 4, 5. Then 10 to the negative 9, then 10 to the negative 13, then 10 to the negative 16. Although that one, I wonder if that's numerical error, because you would expect 10 to the negative 17 there. We could be dealing with some pretty small numbers and leading to numerical error down here. That's why that one's maybe not fitting the pattern. But that's generally what happens is if n increases by a factor of 10, the error will go down by a factor of n to the 4th, 10,000. 10 to the 4th is 10,000. I didn't have to increase the value of n by 10 each time. I could have increased by something else like 3 each time. Maybe first 3, then 9, then 27, then 81, then 243. If I did that, the fact that I'm dividing by n squared in these two means as n increases by a factor of 3, the errors go down by a factor of 9 for those, 3 squared. And for Simpson's rule, if n keeps increasing by a factor of 3, the errors keep decreasing by a factor of 81, 3 to the 4th. So there's nothing special about increasing by a factor of 10. It's just easier to think about. Okay? So that's a very quick summary of things I do want you to know. They were in the extra video, and I go through them slower in the extra video. I did want to talk about Monte Carlo integration. I think I'm going to save that for next Tuesday. It's kind of a fun method for doing integration, including for double integrals or even higher dimensional integrals. I will leave it in the notebook if you want to look at it before next Tuesday.